So logarithmic family of functions, yes.
I have a quick question.
Sure.
So because we're going to be going over chapter 7, are we going to be doing all the homeworks for chapter 7 or no?
We will be going over chapter 7, just not in depth. So that's actually a good question. I may actually need to take some of the homework problems out from chapter 7 because yeah, we won't have time to go as in depth as we normally do. So I probably, if you haven't started working on chapter 7, don't go, because if you start working on it, then I cannot make changes. So if nobody has access chapter 7 homework yet, I can go in and make a change. So yeah, I'll make a note to myself and make sure I make that change. Okay. All right. Anybody else? Anything? Okay. If you think of something, do let me know. Okay. So remember when we're talking about the family of functions, that means we're moving our graph horizontally, we're moving it vertically. You can stretch and shrink your graph, and of course that also includes reflection in there. So just looking at the general form for the family of functions, you can see again, since we use the letter A to represent the base of our logarithmic function, we're using the letter B to again talk about the stretching or the shrinking. And again, if B happens to be a negative number, that's when we're looking at a reflection. If B is greater than 1, that means our graph will stretch. If B is going to be a fraction value or a decimal between 0 and 1, your function shrinks. And then, of course, the h value is what makes our graph move left or right. So if it's positive h, which means you will have x minus 3 or x minus 5, whatever it might be, your graph is moving to the right. If h itself is a negative value, which means you should have x plus some number, that's when your graph is moving to the left. And then, of course, positive k makes the graph go up, negative k makes the graph go down. So looking at our example here for number 11, f of x equals negative 3 plus log of x plus 2. What kind of transformation do you think is happening with number 11 here? So what kind of changes should we expect from the base graph to this transformation to happen? Are we seeing a stretching or a shrinking? Are we seeing horizontal movement, vertical movement, reflection? It's reflected, okay. What else? Can be that hard. What's the x plus 2 telling us? The graph is moving to the left, okay. And other than the reflection, what else are we seeing? What's the 3 telling us? It's stretching. Okay, so here's the one thing you gotta notice. When it is b is multiplied into the logarithm, right? It's b times log of base a. What's the symbol right here between the 3 and the log? A plus sign. So that actually means what they have done is they've taken this k term and they have put it actually in the front. So this is not representing reflection or stretch. That's actually talking about your graph moving down by 3 units. And that's something we really got to be careful about, because a lot of times with these logarithmic functions, instead of putting that minus 3 at the end, a lot of times they will put it up in the front and then look for what is the sign right there before the logarithm. Because if it was going to be stretch or shrink, that should have been a multiplication. But since that's a plus sign, that's actually negative 3 for the k value and negative 2 for the h value, which means our graph is moving 2 units to the left and 3 units down. Okay, so that's actually the transformation that's happening here. Now, what base does this logarithm have? Yeah, it's a base 10 function. So that means we're actually taking the original base 10 function and making this transformation happen. So let's take a look at how this change will end up looking like. So this will be number 11. So remember, our basic function is just the log of x function that is being transformed by moving it 2 units to the left and 3 units down, okay? So remember again, as I was mentioning earlier, when we're talking about graphing logarithmic functions, we normally graph the exponential function, draw its reflection to get the logarithmic function. So we're not actually going to draw our exponential function, but I am going to use that to come up with our table for the base function for the log of x. Okay, so again, remember, anytime we do a table, you can use your 5 points. So if I put that in for my 10 to the x function, what am I going to end up getting? 10 to the negative 2 will give us what? I believe we have done something like this before. 10 to the 0, of course, will be 1. 10 to the first power is 10. 10 to the second power is 100. So if we just switch our x and y values, we should get a table for our base 10 logarithm function. Okay, because we want to see how that transformation happens. So come up with your table for the logarithmic function. Now, once we have that, now we need to see how the transformation creates a new table for the -3 plus log of x plus 2 function. So remember what we said, our graph is moving 2 units to the left and 3 units down, which means from each of the x values, we need to subtract 2. So what will be 0.01 minus 2? So from each of these x values from the logarithmic table, we're subtracting 2 from the x, and we'll actually be subtracting 3 from the y values to get the table for that transformation function. So again, what is 0.01 minus 2? Come on, people.
1.99.
1.99?
Negative 1.99.
Negative 1.99, thank you. Okay, let's go ahead and do all the x values first. So again, 0.1 minus 2.
Negative 1.9.
Negative 1.9, of course. 1 minus 2 will be negative 1. What will that be? 10 minus 2 is 8. 100 minus 2 will be 98. Okay. From all of the y values, we're going to subtract 3 because remember, our graph is also moving down by 3 units. So that's going to be negative 2 minus 3, which is negative 5. Negative 1 minus 3, negative 4. 0 minus 3 is negative 3. 1 minus 3 will be negative 2. And then, of course, 2 minus 3 will be negative 1. So that we're able to see how the transformation happens, we'll graph the basic function log of x, and we'll also graph our transformation function. Okay, so let's see. right, let's do our base function first. So that was the 0.01, -2, 0.1, -1. We had 1 and 0, 10 and 1, which would be somewhere over here. So this graph should be going down this way. Basically going like this. And if you look at the other graphs that we had done, you can kind of verify that shape, right? Just a base 10 logarithmic function. So when we do our transformation, that means we are looking at, well, approximately -2 and -5. So -2 and -5. Somewhere over here. This one again, still at -2, but a little bit further away at -4. So these points are going to be pretty close to each other vertically. Then we have, and my table's a little off, but we should be at -1, -3. So right about here. At +8, we are at -2. And I didn't actually include that, but to see where we cross our y-axis at, you're going to be at -2.699. So if you want to know kind of where we're going to cross the y-axis at. If it helps, you should remember that since our original function log of x has a vertical asymptote at the y-axis, x equals 0. Since our graph moved 2 units to the left, that means our vertical asymptote also moved 2 units to the left, which means we actually have a vertical asymptote right here at x equals 2. And that's why these guys were getting closer and closer to -2, is because you're hitting that vertical asymptote. Okay. For this transformation function, what will be our domain and range? What will be the domain for -3 plus log of x plus 2?
Parentheses, -2 to infinity.
Yeah, because again, our graph moved 2 units to the left. So like I said, our vertical asymptote also moved 2 units to the left. So instead of being at 0 to infinity, not including 0, we're at not including -2 to infinity. What about the range, the y values?
It's going to be -3 to infinity, right?
Yeah. Negative to positive infinity. And remember, it's this function in green that we are talking about. Alrighty. And you know, the easiest way to see that our graph has transformed is actually using this ordered pair right here, 1 and 0. So that is the point that moved 2 units down, and then it moved 3 units left. So that's that point which basically got moved. You can kind of verify it that way. So just what your transformation for the family of logarithmic functions will look like. Questions on number 11? Okay, so just as a process, we first created the table just for the 10 to the x function, and then inverted our x and y values so we could get a table for our base function of log of x. Once we got the table for our log of x functions, then from each of the x values, we subtracted 2 since our graph is moving 2 units to the left. And then from each of the y values from the log of x function, we subtracted 3, since our graph is moving 3 units down. And that gave us the new table for the transformation function. And then those were the points we used to graph our function here. Okay. This next part here is just talking about how to solve logarithmic or exponential equations. So we're saying some equations involving logs can actually be solved by writing them as equivalent exponential functions. And then, of course, some exponential functions can be solved by writing them as equivalent log functions. So let's take a look at how we can solve something like number 12, which is log of w with base 4 equals 7. And of course, we're trying to figure out what that value for w could be. So since this is given to us in the logarithmic form and we can't really solve log of w, we will need to convert this into exponential form. So again, just to jog your memory, you take the base that's on the logarithm, which will become the base of your exponential function. Remember, a log always gives you an exponent, which means 7 is actually the exponent of base 4. And this will equal this value of w. You can see once you get it into this form, it's pretty straightforward what w will be. So what is 4 raised to the 7th power? $16,000. Go ahead. 384. And you've got your W. Okay. And we had kind of seen this at the beginning when we had looked at how to go back and forth between exponential and logarithmic form. So we're actually kind of bringing that back here to solve this. Did anyone have questions on 12? Okay, so now you can see for the next one, they are asking us to find the inverse for this function, f of x equals 3 times e to the power of 5x minus 1. Now this one's actually going to be a little bit interesting, the way we solve it, because when they're asking us to find the inverse, that means we're trying to find its logarithmic equivalent. So the easiest way actually to convert this and find its inverse is going to be our switch and solve method that we had seen back in section 2.5. So to find the inverse, the first thing we're going to do is replace our f of x with y. Okay. And remember, the switch is where we actually interchange our x and y places. So where I have y, I write x. Where I have x, I replace it with the y. And our goal now is to try and get that y by itself, try and isolate it. So before I can get to the y, that actually means I need to isolate that whole e raised to the power of 5y minus 1, which means let's start by getting rid of the 3. So since this is 3 multiplied into e, to get rid of it, we're going to divide both sides by 3. Okay? And I actually prefer to write it as 1/3 x. Because again, you just never know when we may need to get x by itself or something like that. If not, you can leave it. Okay. Now your 5y minus 1 is in the exponential level. For us to be able to isolate the y term, we need to bring it from the exponential down to the base level, which is where we're actually going to introduce logarithms. So since this is a base e, right? To get rid of a base e, we need to bring in a base e logarithm, which happens to be our natural log. So to get rid of that base e, we're going to take a natural log on both sides of our equation, which means I end up getting natural log of 1/3 x on the left and natural log of e to the 5y minus 1 on the right. And the reason we do this is because natural log also has base e, and of course our exponential term also has base e. We had seen this in one of our examples that we had done before. If your bases end up matching or being the same, they essentially basically clean up, leaving you with just the exponent. So what's happening is the natural log is essentially canceling out this base e here, leaving us with 5y minus 1. And you can see by doing this, we got it from the exponential level down to the base level. And then, of course, we've got our natural log of 1/3 x on the left. And now you're just getting y by itself. So start by getting rid of the 1. Since it's minus 1, go ahead and add it to both sides of your equation. These guys here will cancel out. And we end up with natural log of 1/3 x plus 1 equals 5y. And again, to get y by itself, divide everything by 5. Okay. Instead of leaving this with this whole mess that we have here, divide by 5, I'm actually going to write it as 1/5 on this whole thing of natural log of 1/3 x plus 1. And then once you get y by itself, normally we replace it with our inverse notation, but with logarithms we don't really use that inverse notation. So you can essentially, since we're using f of x for the original function, let's just use g of x here. 1/5 and this will be your inverse function. So basically, as you can see, we're falling back on what we had learned back in chapter 2 when it comes to finding inverses, is using the switch and solve method. Now the second question, number 13, was more in a generic sense. Number 12 was where we were actually trying to solve for w and figure out what the value of w could be. In this one, like I said, they're doing it more in just general terms, but a lot of times this is what's going to happen when we are solving an exponential equation. We may need to convert it into an equivalent logarithmic equation to solve it. So that's something we will be looking at as we go forward in this chapter. Any questions on number 13? So just finding the inverse by using our switch and solve method, okay? So we had talked about the one-to-one property in exponential functions. Obviously, if exponential functions are one-to-one and logarithms are their inverses, naturally that means logarithm functions are also one-to-one functions, so they will also have a one-to-one property. So here the idea is, if you have two logarithms that are equal to each other with the same base, so I've got base a on both sides of my logs, if this is going to be true, then that means the value of our logs is also going to be equal to each other. So x1 will be equal to x2, or they're basically saying if two quantities have the same base a logarithm, then those quantities have to be equal by this one-to-one property. You know, which really comes in handy when we're trying to solve these kind of equations here. But the more straightforward process we're going to use here, instead of using the one-to-one property, is actually fall back to convert them into exponential notation and then simplify these equations. So we've got log of 2x with base 5 equals -3, and of course we're trying to figure out what that value of x will be. So this guy is Okay, so if we're converting this into exponential notation, what are we going to end up with?
2 plus x, or x plus 2.
X plus 2. You're just converting it from the logarithm to the exponential notation.
I'm sorry, I'm thinking x plus 2 as the actual exponent itself.
5 to the negative third equals 2x.
Yeah, so you're taking the base 5 raised to the exponent of negative 3, and that will equal 2x. So just converting it from a logarithm to an exponential notation. Now, what is 5 to the negative 3? And leave it as a fraction. No decimal. Remember, if it's a negative exponent, to make it positive, put it in a denominator of 1. So what is 5 to the third then? 125. And then to get x by itself, we need to get rid of the 2. So technically we divide by 2, but since I have a fraction on the left-hand side, I'm actually going to multiply both sides by 1/2. These guys on the right-hand side cancel out. 1 times 1 is 1. What's 2 times 125? 250. So 1 over 250 is our x value. Do not put them as decimals, okay? Leave them as simplified fractions. I think that's the one common thing I've usually seen is students trying to convert it to decimal and it not working out. So just be kind of mindful about that. But that's all you have to do. So start by taking the logarithm, convert it into an exponential form. Now, since we had a negative 3 as our exponent, we're putting it in the denominator of 1 to make it positive. Then you get 5 to the third, which is 125, 1 over 125, and then divide both sides by 2. And you know, some of your calculators will let you convert decimals to percent. So you can try using that also. Obviously, something similar happening on number 15. We've got log of x with base 3 equals 1/2. So again, convert it into an exponential format and try and find that x value. So again, as exponential notation, what will this look like?
1/2 x.
Yeah, 3 to the 1/2 equals x. Remember, exponent of 1/2 is the same thing as square root of 3. And I would actually leave it right there. Because if you try to do square root of 3, you're going to end up getting a decimal answer again. If they ask you for decimal approximation, then you can do that. If they say give an exact answer, you want to leave it right here at square root of 3. Okay. So now we're actually given exponential notation. You have 3 to the power of x equals 77. And again, we're trying to figure out what that x is going to be, which actually means now we'll need to convert it into a logarithm to find our x value. So for number 16, if I am rewriting this into logarithmic form, what will that look
Log is 3, 77.
Very good. Equal 2x. At this point, we haven't officially talked about the base change formula. So we're actually going to leave it right at this stage. Now, I know some calculators will solve bases that are different from natural log and a common log, but we're assuming that we cannot solve this at this point, so we're going to leave. This is your exact answer. If they wanted a decimal approximation, that's where a calculator answer would come into play. So this is your exact answer. Okay? What do you think is going to happen on the next one? 10 to the x equals 25.
If we just log 25 equals x.
Oops, sorry. Hold on. Okay, go ahead, Trey.
Would it just be log 20, log and then parentheses 25 equals x?
Yeah, pretty much the same exact thing what we did for number 16, but the difference is this was base 3, so we actually write the base 3. For number 17, since this is base 10, remember common log, it's understood to be base 10, so you don't have to specifically say base 10 on that one. And again, if they want exact answer, leave it here. If they want a decimal approximation, since log 10 is something your calculators can do, you just plug in log of 25 and you'll get some kind of a decimal answer for that. So again, if they're asking for exact answer, leave it right here. Okay. All right, I'll give you guys about a minute and let me see what you come up with for number 18. E to the power of 2x equals 3. And leave it as an exact answer. Again, don't do a decimal approximation. So if your exponential is base e, what logarithm do you use?
Natural log?
The natural log, yeah. Okay, and the natural log will be of what number?
3.
Natural log of 3. And remember, a log always gives you the exponent. So whatever is the exponent on the exponential form is what your log will always equal to. Again, if you type in natural log of 3 on your calculator, you're going to get some kind of decimal answer. So leave it as natural log of 3. To get x by itself, divide both sides by 2. And you're going to end up getting, again, x equals, you can do 1/2 natural log of 3. Okay. Questions on number 18? Okay. Again, if you wanted to look at different types of logarithmic functions, there's a function gallery in your textbook. Now, this last one here is talking about, I think we had seen something similar in the previous section. So here we're talking about how long does it take for $4 to grow to $12 at 5% compounded continuously. So this time we're actually asking you to find the time. How long will it take $4, which will be the amount we initially started out with, so that's our principal. It's growing to $12, so that's our future value or the amount. They're telling us it is growing at a rate of 5%. So 5% as a decimal is what? 0.05, and they're actually asking us to find the time because they're saying how long does it take, right? Now, they're also telling us your rate is being compounded continuously. So if it's compounded continuously, this is the compound interest formula you're looking at, right? The PERT formula. If they told you it was compounded annually, semi-annually, quarterly, that's the formula with the N. that you have to use. A equals P, and then in parentheses 1 plus R over N, and that parentheses is raised to N times T. Again, you can look at that formula in 4.1 handout. So compounded continuously is the formula which has the natural number E. So if we plug in all these numbers that we know, A is 12, P is 4, E is raised to the power of 0.05, and T, of course, is our unknown value that we're trying to calculate. And so you can see why this example shows up in this section, because our unknown value T is in the exponent. You can only use logs to bring it down from the exponent to the base level. So this was something we couldn't have done in the previous section with exponential functions. We can only do it once we get our logs. So very similar to the examples, what you basically did in 16, 17, 18, kind of that sense, but now trying to figure out what T will be exactly. So the first thing I want to do is isolate that whole exponential part, E raised to the power of 0.05t. So I need to get rid of the 4 since it's 4 times E. Divide both sides of your equation by 4. What is 12 divided by 4? 3. Alrighty. Now that I have that whole E raised to the power of 0.05t on one side and 3 on the other, now we need to bring it from the exponential to the base level. That's where, again, we introduce our logarithms. So since this is base E, obviously we need to bring in a natural log again. So you end up getting natural log of 3 on the left-hand side, natural log of E to the power of 0.05t on the right-hand side. Just like we had seen in our previous example, the natural log and base E will cancel each other out, leaving us behind with just 0.05t. Right, so now our T goes from exponential to the base level. To get T by itself, divide both sides by your 0.05. Now we obviously need to get an approximate answer, so we cannot just leave it like that. So this is where you will plug this into your calculators. Be careful and make sure if your calculator naturally opens parentheses after the natural log, close it before you type in the divide by 0.05. Because otherwise your answer is not going to come out to be correct. Can you tell me what that raw answer comes out to?
21.9722.
Okay. So I'm actually going to show you 2 different answers that you can get from here, because it's going to depend on what your instructions say. If your instructions are only looking for answer in years, then of course 21.9 will round up and 22 years. So we're basically saying for your money to go 3 times from $4 to $12 at 5%, it's going to take it approximately 22 years. But sometimes they will ask you to round it to the nearest day. And if they ask you to round it to the nearest day, that means I've got 21 full years. But then how many days is this going to be? So this is where we actually take just our decimal part and multiply it with 365. So the first thing you should actually do is you should still have 21.97224577 or whatever decimals you're calculating. Subtract the 21 from it, because we know that's 21 complete years. So we actually don't need this as part of our calculation. So go ahead and subtract that 21 from your calculator. And then you should have just the 0.9722 whatnot left behind. Take that number and just multiply by 365. And that's actually coming out to be 356.5 54.86, which will actually round to 355 days. So your answer will either be 22 years or 21 years and 355 days. So you just kind of have to look at your instructions and see what kind of rounding they're asking you to do. Each problem has its own different way that they're going to do. And I think we're going to look at some examples in the next section. So questions on, what was this, number 19? So just as an application of a logarithmic function.